right, it's 8 o'clock here on the Pacific Coast. Good morning, good afternoon, good evening, everyone. Welcome to our next installment of tinyML Talks. My name is Ravi Sivalingam from Qualcomm AI Research. I'll be your moderator today. I'd like to thank our tinyML Talk sponsors, DeepLight, Kixo, Edge Impulse, Reality AI, Maxim Integrated, and SynSense. Additional sponsorships are available both for the global tinyML Talks as well as for the local tinyML Talks. Please contact Betty at tinyml.org for more info. Our upcoming next tinyML Talks are on Tuesday, September 15th. We have Hiroshi Doyu from Ericsson Research and Vikran Tomar and Sam Meyer from Fluent.ai. Same time, 8 a.m. Pacific, 2 weeks from now. Please contact talks@tinyml.org if you're interested in presenting at any of the global or local meetups. I do have another announcement. March 22nd to 23rd of 2021, we have the next tinyML Summit. The call for presentations and posters for the summit are out at tinyml.org. This time around, we have a research symposium on day 2 of the summit, and the call for papers are out on the website as well. Please visit tinyml.org for more details. Deadlines for submission is November 2nd. Just a reminder to everyone, the talk video will be posted on YouTube and the slides will be posted on our forum page by tomorrow. So you can view that as soon as it's out. You'll get a notification. And if you have any questions, please do ask them in the Q&A box and not in the chat box, because I'll be observing the Q&A box and asking questions throughout the talk. All right, let's get to our first speaker today. Suren Jayasuriya from Arizona State University is going to present on towards software-defined imaging, adaptive video subsampling for energy-efficient object tracking. Suren Jayasuriya is an assistant professor at Arizona State University, School of Arts, Media and Engineering, and Electrical, Computer and Energy Engineering. Before this, he was a postdoctoral fellow at the Robotics Institute at CMU, and he received his PhD in Electrical and Computer Engineering from Cornell. His interests are in computational imaging and photography, computer vision, graphics, machine learning, and CMOS image sensors. Take it away, Suren.
Great. Thanks, Ravi, for the introduction, and thank you to the tinyML community for sponsoring these talks and inviting me to present. I'm really excited to present this work to the tinyML community. I'm very interested in research across the stack, vertically oriented research, and I think what you'll see in this presentation is going all the way from devices and sensors through systems, through algorithms, and really understanding how we can coordinate research and integration efforts across the stack. And in particular for this talk, I'm going to be introducing this newer idea of software-defined imaging and the opportunity it's available. So I'll give a kind of overview of software-defined imaging, give some examples from my lab of what we've done in different spaces, and then I'll talk about the specific problem of energy-efficient object tracking, where I think the ideas of the tinyML community and software-defined imaging can be useful. So to start off with, I think that some motivation that might not be so needed for this community here is the advances of machine learning, and particularly in visual AI or mobile computer vision. So here we have tasks like object recognition, 3D structure for motion, localization and mapping, they're very commonly used in robotics, face recognition, activity recognition, and higher level semantic tasks. And the research has gotten so advanced that we want this always on, and we want it on our mobile devices, on our embedded platforms, on our computing platforms, and we want it in real time. And so it's a very cool idea. It's a very exciting time to be a researcher in this time. But one of the main things is one of the main bottlenecks to realizing this vision, especially on the embedded platforms, is energy efficiency. And that's what the tinyML community is primarily concerned with. That's what a lot of communities are interested in solving to make these applications work out in the real world, out robustly in the wild. So how have people been trying to tackle this problem? This is a very interesting problem. Most of the research to date, of course, there are many exceptions to this, but a lot of research has been trying to reduce the computational cost of machine learning. So the algorithmic efficiency, things like quantization of the networks, pruning, compression, all types of software-based and systems-based work aiming at making the computational workloads more efficient, faster, and low power. Hardware efficiency, so not just in the software realm and the systems realms, but building new types of chips. And we've seen a great improvement in the amount of application-specific integrated circuits, ASICs, devices, CPUs, GPUs, and also ASICs that are doing, and as well as new emerging things like neuromorphic, and even the talk after me from BrainChip has some really exciting hardware that you're going to hear about. But one I'm focusing on this talk is actually the input side. So what about the imaging itself? How can we actually make the sensors more energy efficient and be able to work well with the back-end optimizations that a lot of people are doing to make tinyML vision possible for vision? So what's one example? Mobile devices get really limited by their battery life. So this was a study, a little bit older study by my colleague Robert Likamwa from Arizona State. They took the Google Glass and they ran continuous face detection, the Viola-Jones face detection algorithm. And what they showed was that within 40 minutes of running this continuous face detection algorithm, the Google Glass ran out of battery. Of course, this was a couple of years ago, and it wasn't even a deep learning based machine learning algorithm. It was the Viola-Jones, kind of a more classical face detection algorithm. But the 40 minutes of battery life, and when they did energy profiling, image sensing, which here we're talking about image sensing, we're considering both the operation of the sensor and the communication of the image data off the sensor to the rest of the system. That took up 50% of the energy costs, and then the computation took up the other 50% and the overheads. So clearly sensing, input sensing is, for particular cases, can be quite an issue. And especially as we do a lot of work to make the computational backend more energy efficient, it's going to turn out that our sensors are going to be more and more the bottlenecks. And so we need to do research on both sides of the equation and integrate them together. So one kind of classical question could be like, why not use the power of cloud computing? Why not offload your computing power? Well, this is some numbers actually from Jonathan Ragg and Kelly's thesis that shows that basically communication costs are orders of magnitude more expensive than sensing, which are orders of magnitude more expensive than local computation on the device. So for a single ALU operation normalized, reading from an image sensor is 4,000 times more expensive than a single ALU operation, and sending over LTE communication is even more, 50 million times. So clearly, like, we need to do this, any kind of, if you want to get to the low power that the tinyML community wants in the milliwatts or lower, you really can't rely on communicating to the cloud to do your processing without some, smart thinking or some new technology improvements in that side of the domain. So we need a solution that reduces energy for both image sensing and data communication. So the focus of this talk is going to be this idea of software-defined imaging. And really, the theme is how do we utilize the fact that our sensors are programmable? They are parameterizable. They've been designed with some flexibility. How do we use them effectively in our algorithms and systems design so we don't lose those benefits when they go back all the way up to the stack to the end application? And I really like this problem because it brings together a big community from programming languages, operating systems, down to analog and mixed circuit signal design and computer vision applications. So I don't have a definition for you of software-defined imaging. I think like putting a formal definition would make it restrictive and so on. But you could think of it as a parallels to the work in the 90s and the 2000s of software-defined radio. So as radio receivers became flexible in that their hardware could be programmed, the filters, the front end, the LNAs, the oscillators, the mixers could be programmable. Similarly, software-defined imaging wants to express those same kind of ideas, but for CMOS image sensors. So as image sensors are getting mechanisms that are becoming more programmable and able to be reconfigured on the fly, things like resolution, things like region of interest, exposure, quantization, we want to understand how can we use this paradigm to help improve the energy efficiency of the total visual system, and particularly for machine learning workloads, because that's one of the main now emerging and applications of image sensing. So let me show you two examples from my lab of how we've started to push this software-defined imaging paradigm before I launch into the main topic of this energy-efficient object tracking. So this was a paper called Reconfiguring the Imaging Pipeline for Computer Vision, presented at the International Conference of Computer Vision 2017. And the idea was that we wanted to look at this chain from photons through the raw sensor to the raw sensor data. It then usually goes through something called an ISP, an image signal processor or image sensor processor, and then forms those JPEG or compressed images that you're used to dealing with if you're on the software side. And this project really looked at what happens if you make this pipeline from the sensor to the compressed images programmable. What kind of opportunities and affordances does that allow? So here, just for background for people who don't know, and this the sequence of image processing operations applied to a camera ISP. Now, this is not all of them, and different camera companies and sensor companies have their own proprietary chains, but most of them involved an analog front end after sensing through the optics and the color filter array of the pixels to do amplification and digitization. That coming off the sensor is called the raw image. That raw image then goes through a series of operations like white balancing for color balancing, color filter array demosaicing to account for the Bayer, commonly the Bayer pattern or whatever color filter array you have on your sensor, denoising to help improve, especially in low light situations, tone reproduction, gamma compression, and then regular JPEG compression to give you your final 8-bit or if you want higher bit image. So all of these operations, which I'm representing here on the left with this stack, for instance, are done through this digital chip. Sometimes it's an SoC on the chip, sometimes it's a separate chip, depends on the design. But images coming right off the sensor, they look dark, they look mostly green because of the Bayer pattern. They are not visually pleasing. And then the ISP spends a lot of effort to make images look good. So you can see here on the left a representation of the raw images, and in fact this is even brightened so that it's even able to be displayed. It's actually even darker than this. And then you see after the ISP how much work goes in to make it look really good. But the question that is kind of interesting is how much of this processing is needed for deep learning versus human consumption. So we wanted to explore this idea and see how can the software dictate what the ISP parameters should be. So we did a bunch of things where we actually converted JPEGs back to PNGs using some existing research. There's some some software to be able to do that, and we ran different experiments turning on and off different stages of the ISP to test the sensitivity of the algorithms to different ISP blocks to say, is demosaicing necessary? Is denoising necessary? Or could you turn them off, save energy, and still get pretty good performance? Here's some insights. I'm just going to present some of the insights of the results we found. One thing is light actually follows what's called a log-normal distribution. So most of the light is in our natural scene is clustered in the lower end of the spectrum. So when we quantize in a sensor, we usually quantize uniformly, but this is actually not the most efficient use of the bits. In fact, it's better to actually normalize the PDF or normalize the probability distribution function before you do the sampling. This is typically actually done digitally through the gamma compression. The gamma compression kind of acts like that normalization because that's why our eyes are sensitive to logarithmic changes of light. It's because biologically our visual systems have been adapted to this. So this idea is something that we noticed that ISPs reproduce to help give good performance. So the way to implement this is idea is logarithmic quantization. So using non-uniform levels, but levels based on the logarithmic curve, actually showed that we were able to get better performance even though we stopped the bits down. So going from 8 bits down to 5 bits, you can see in the center graph, we are still able to get pretty flat errors. Without the error blowing up, we're able to save energy by going to less number of bits, which means, especially if you use something like an SAR ADC, less number of tap switches or current on the capacitors, and you save energy there. And in fact, there's even a more optimal way to do this, something called the Lloyd-Max algorithm, where you can design your non-uniform quantizer that's optimal up to a MSE loss function for the particular distribution you're interested. So this is an idea of tailoring your quantization for this. So just a summary of this paper, we found that demosaicing and gamma compression were very important for ISPs, and that the use of logarithmic quantization helps save energy. Further, if you read the paper, we actually do some mixed signal circuit design to approximate the ISP, so we can actually turn off the ISP and approximate it in the mixed signal domain using things like binning of pixels, as well as a logarithmic ADC design. So I encourage you to read the paper for more information. And even there's some newer work on this where we actually applied these ideas to a visual SLAM pipeline. So this is a very common robotics algorithm, and we proposed a new gradient-based quantization scheme where we looked at the images and said, what if the images were spatially quantized different? So regions with flat regions with no texture, like a blank sky that's pretty clear, you're not going to get many computer vision features. You want to quantize that low to save energy, so that you save your bits for the features that are going to be useful for your tracking. And so I encourage you to also look at this follow-up work that's going to be presented at ISIP, the International Conference of Image Processing 2020, where we applied this to visual SLAM. Just one more example before I go into things of like idea of where you can even get down to the sensor level is my PhD work with Al Molnar from Cornell University. Is we looked at these integrated diffraction grading pixels called angle sensitive pixels. The idea was that if you put two metal gratings on the order of wavelength of light above the sensors, you can preferentially block certain angles of light, and due to the diffraction of light that hits these gratings, and this would be able to give you angle information. And it turns out that if you tile the image sensor with these different gratings, like a color filter array, you can actually do optical edge filtering. So it's a little bit complicated, but basically you can these pixels can act like an optical edge filter and give you for free computation in the optical domain, and that's very low power. This was showed by Wang et al. In a Custom Integrated Circuits conference in 2012. What we did is we took this as the front end for a computer vision deep learning pipeline. And this is called ASP Vision, where we optically compute the first layer of the CNNs by noticing that the ASPs are a really good energy efficient way to compute that first layer activations. So the sensor, it's a real working prototype, works at 2 milliwatts of power and does low power digit and face recognition. In our very simple examples, greater than 90% accuracy while doing this optical edge computing. So I encourage you to read this paper in CVPR 2016 if you're interested in more ideas. So maybe I'll pause here, and you know, I talked a little bit about sensor changes and do that, and I'll allow maybe if there's some questions about that before I launch into the idea of how do we design algorithms around our cameras.
Yep. I have a couple of questions. One is, what operations do you think could be moved to the mixed signal domain in order to take advantage of, for example, analog computed memory schemes?
Yeah, that's a great question. I think there's a lot of interesting research here. So convolutions and anything you can do. There's a really interesting type of circuits called translinear circuits where you can do multiplications and different kinds of arithmetics in the circuit itself. There's a lot of work with doing that. Victor Groove from UIC had done a lot with focal plane array processing. The other thing is like there's a lot of work with like CNNs and memory. There's a lot of in-memory compute. Robert Lee Como, who I mentioned, had done a work called Red Eye, where he built a CNN into the fabric of so on. There's other works that are building it into the ADC, like doing the multiply accumulate operation in the ADC and the like SVMs and the ADC. And so I think there's some very interesting things of baking the computation, especially computations that you use a lot, like convolution or dot product, directly into the either the analog sensor or into the memory.
Got it. Got it. Thank you. One other question, are there other sensors that could be used prior to the 2D camera sensor, example like a PIR, that could minimize energy usage before a subject appears in front of a camera?
Yeah, so this is a great idea. I call these ideas based on some work from Deepak Ganesan in University of Massachusetts Amherst called cascaded pipelines. So like you could have a cheaper sensor that's just like a like, hey, there's something here. You should maybe turn on your main sensor. So there is some system work there. Later I'll talk at the end. I'll just talk very briefly about event-based cameras. I think there's a real opportunity for that. What would be really even cool is if you could put this into heterogeneous image sensors. So you have the image sensor, single die, where you use maybe some sparse set of pixels for these detected or activity pixels, and then the main image sensor for your primary visual compute, so on. And I think that's a emerging area of research, and of course there are barriers in terms of the technology and how to design it, but I think that's a very exciting direction we're trying to move towards.
Great, thank you. We'll
Okay.
continue the rest of the questions.
Thank you. So continuing on, let's talk about going up higher in the stack now. How do we design new algorithms to work efficiently with our cameras? And for this, I'm actually going to focus on the problem of object tracking, because I think this is one of the fundamental payloads of computer vision. Everyone wants to do object tracking. It's one of the things needed for robotics, autonomous driving, surveillance, so on. And these tracking systems are like the Olympic challenge, right? There, you need energy efficiency, but you also need speed, you need low power, and it needs to work all, without communicating to the cloud and working at the edge on the devices, so on. And so with this, what we have started to look at in our lab is how can we use the ROI capability of sensors. ROI means regions of interest. So most image sensors, or at least most modern image sensors, have the capability to read out only a subset of their pixels. Now, usually these are rectangular selections, so there has been in the research and maybe some cutting edge image sensors, ones that can do arbitrary shapes to read out, but basically by controlling the addressing and the readout of the image sensor, you can actually save power by turning off other pixels. You can also reduce the amount of image data transmitted, so you save data in communication costs off the chip and onto through the ISP, and in computation because the ROI is smaller. So here's an example of an image that, given a sensor mask which is sent to the image sensor, then it reads out what the image would be. So it doesn't actually read out that original image, it actually reads out the subset image directly. And so the question we were interested in is, how do we have the sensor intelligently pick the ROI patterns for the next frames given the frames it's already seen? So you can imagine tracking an object moving across a frame. I only want to read, for a single object, I only want to read out that single object. I don't want to worry about other things in the scene. I just want to optimize my energy cost for tracking this one object. So this is our solution. Our solution uses a lot of existing algorithms that have been proposed in the literature, but this new idea of doing joint object tracking and subsampling to predict the next frame that we should subsample is kind of unique here. So just to walk people through this diagram, you have this image comes in and it gets subsampled by some mask. We then feed it to some detection and tracking algorithm. So here we're using tinyYOLO or a mean shift tracker, depending on your computational needs. And we'll talk about what we use here. And then we assume the box that you get, the bounding box that outlines where the object should be, we are going to treat that like an object itself and use the principles of Kalman filtering. So if people are not familiar with Kalman filter kind of, you can apply a physical model, for instance, like a simple physics-based velocity acceleration model to the thing that basically tries to map out the trajectory of the object. So basically, our algorithm is designed to extract the object bounding box and predict the trajectory of the objects to then feed the sensor mask to say, hey, if I predict the object is moving in a certain direction, anticipate that and sample the bounding box at this next frame. So this is a very simple idea, but it's a closed loop control loop for the image sensor that puts the sensor in the loop. So you need to communicate with the sensor to subsample the image and do this. And the key is there's a lot of interesting questions of when do you sample the full frame versus when do you go into this predictive tracking mode and so on that we want to evaluate the energy efficiency of. And so this is work that we are presenting at the ICIP 2020 conference, Design and FPGA Implementation of this algorithm. And this whole problem is what we call adaptive video subsampling. The idea is that as the video changes, you want to change your subsampling patterns in order to still preserve whatever vision task you want to do. In our case, we're doing tracking, but you can imagine you could do it for classification, you can do it for other things, and the subsampling behavior would change. So the simulation results, we tried this out with 20 single object tracking videos, and we are reporting something called the mean average precision. And our metric for energy right now is very coarse in the simulation stage. We're just considering the number of pixels we turn off or subsampling, because that roughly corresponds to energy savings in the sensor at least. Of course, a more fine-grained energy analysis is warranted here, and we're starting to work that as we build our hardware infrastructure. And you can see here that the mean shift plus Kalman filter and the neural network, or the tinyYOLO plus Kalman filter, is getting around 73 to 76% mean average precision, while turning off 70 to 80% of pixels, compared to a baseline method that was considerably lower. I know the image on the bottom right is a lot, but if you look at this hard example, the mean shift plus Kalman filter was able to isolate this biker riding very small compared to the full background, while the other methods were having a little bit of difficulty. So you can see how ROIing can really help zoom in or foveate. There's a very interesting parallel sets to work on foveation sensors, but you can basically foveate to the object you want to look at. So we accelerated this algorithm, and we actually leveraged FPGA acceleration for a variety of factors. In particular, we used these Xilinx CCU102 boards, and we used the, well, this is before the new version released, but we used this Xilinx SDSOC software. Now there's a new software called Vitis AI, which looks very promising that Xilinx has come out with. But we were able to use HLS, high-level synthesis. We wrote our code in C, C++, and then we ran it and synthesized it into RTL that could then be put onto the board and tested. So, by the way, we accelerated just the algorithm portion of this. We are still working on actually getting a real image sensor to interface and close the loop to do a full integrated system. Of course, that involves a lot of work to make sure the image sensor can talk to the FPGA and back and forth. But using this FPGA acceleration of the algorithm, we were able to get 26 milliseconds effective latency, or 38 frames per second on a 75 megahertz FPGA with 1080p resolution. And we did a bunch of other things about the resource utilization and 23x speed up in hardware clock cycles. But this was accelerating the mean shift algorithm. But the point that I like to point out here is this was really interesting and shows the possibility of getting to possibly real-time software-defined imaging, which is exciting. Can we do better? I just want to take the last 2 minutes here to kind of point out some emerging work that we're starting to develop, and this is very preliminary, of using reinforcement learning. So reinforcement learning makes a natural sense. You want the AI algorithm to also configure the sensor and make intelligent predictive behavior choices. More so than just the simple Kalman filter, we want to actually go to an RL algorithm. So instead of a Kalman filter, we use an LSTM, so a deep network here, and we train it using a reinforcement learning policy gradient algorithm called reinforce. And this learns a policy to jointly track the ROI and the tracking. So the network architecture is basically using a pre-trained object detector to gather features, and that's fed to the LSTM along with the subsampling matrix information of what was used. And then the policy determines what should be the next subsampling and object location jointly using this. I'm omitting the math here of the policy gradient, but it was just basically the reinforce algorithm applied to train this. And so here's some preliminary results. On the left is our YOLO plus Kalman filter algorithm from before, and on the right is the YOLO plus LSTM trained with reinforcement learning. Now, I don't know how this looks over Zoom, so you might be thinking your image is lagging, but there is actually some blockiness and some flashing, and what's happening is the algorithm has learned to look for a larger region occasionally in the frames to know where the object is moving, and then it focuses back in on the right. While the left, you can see the YOLO plus common filter actually has some trouble with this video, and it is actually not able to completely localize around the player and do so. Partly because the object motion is quite complex and doing a lot of not just linear motion, but more complicated trajectories. But on the right, the reinforcement learning algorithm has learned to predict the ROI and where the object is moving, and then scale back into foveate for energy efficiency. Of course, these are preliminary results, so we want to evaluate the benefits of these RL algorithms and think about how to implement these RL algorithms efficiently onto hardware. And just to kind of conclude, we're really interested in how could things like event-based cameras improve the performance and energy efficiency of this, including extending to like multi-object tracking. So in conclusions, I just want to kind of end with, don't forget about sensors, input side of energy efficiency. Co-designing across the stack is a great opportunity for this community. And this area of software-defined imaging has lots of interesting configurable imaging pipelines, adaptive video solutions. And so I'll end with there. And if there's if you're interested in the papers, feel free to check out my website for some of these work, and happy to answer any questions.
Thank you, Suren. That was really great. We have a bunch of questions. Let's go one by one. Does this tracking work even when it becomes dark or at nighttime?
That's a great question. Obviously, it usually works better in sunlight. It all depends on the performance of the object detection or the feature extraction. And so it is a known problem that when it gets darker, like feature extraction becomes more difficult. And so you need a really good sensor with good noise properties and able to work at low light to do it. So we have not explicitly tackled that problem, but that is a good work to try to make it more resilient.
Great. Next question. Can the adaptive video sampling keep up with the speed of the moving object? There seems to be a maximum frequency limit for the method.
Yes, and that's primarily by the frame rate of your total algorithm, which is why, like, even though your sensor might be working at 200 frames per second, but if you can't compute fast enough, then yes, you have problems. Right now, we have effectively showed 38 frames per second on an FPGA for that backend, which will work for most ordinary objects, but for very fast-paced objects, you probably need a smarter solution. And that's why we think these things like event-based cameras might be the way to go. You might need to break out of that frame mindset. Of course, those have other challenges that you need to solve research-wise, but yes, there is a max frequency. It's dictated not just by the camera frame rate, but also by the total system latency.
Got it. Would there be any limitations if you track more than one object in a given scene, and how does this affect the results?
So for multi-object tracking, the natural extension would be to just increase the number of potential objects you're tracking. Of course, that makes the state space of the Kalman filter, or in the RL, the state space of the latent space larger. So there is a drawback. And at some point, if you're trying to track too many objects, it might be more energy efficiency to just capture the entire object, the entire image itself. So I think that's a very interesting thing we want to look at, is what is the trade-off? Can we just want to make that capability programmable and let designers or application developers decide what is the trade-offs that work for their particular applications?
Okay. Following up on that, when you do have multiple objects that are disjoint in the scene, would you be able to specify multiple ROIs? Do you know if there are any image sensors today that can support multiple ROIs simultaneously?
I don't know off the top of my head. I do know, like, the capability is there. It's been shown in research, like arbitrary ROI capability and so on. I don't know off the top of my head a commercial solution, but definitely the way to address and read it out, it is possible. You probably have to do something with the column parallel readout though to enable that. And so I don't know if you can go today and buy that off the shelf. But I'm projecting in the future that we're going to have image sensors that you can get that capability.
Got it. We'll take one last question, and then we can move the rest of the questions to the forums. In your Kalman augmented object detector, do you adapt your ML workload like tinyYOLO to handle variable resolution inputs?
Sorry, I didn't catch the last part.
To handle variable resolution inputs?
Yes, so it's a fully convolutional YOLO, so it can handle any ROI. going in. There's this notion from machine learning that it's fully convolutional, so it doesn't depend on the input. And the Kalman filter is only working on the bounding box, so it's independent of the resolution. It just thinks of the bounding box coordinates as a single point object and is modeling it that way. Of course, things like deformable motion are not going to be captured that well by this strategy.
Got it. Got it. All right. We have actually a bunch of other questions. Unfortunately, we're out of time, so we'll move these questions to the forum. Please, all audience members, feel free to continue the conversation on tinyML forums. Thank you, Suren. We'd like to thank our tinyML Talk sponsors, DeepLight, Kixo, Edge Impulse, Reality AI, Maxim Integrated, and SynSense. Additional sponsorships are available. As mentioned, please contact Betty at tinyml.org. DeepLight uses AI to make other AI faster, smaller, and more power efficient. Edge Impulse enables developers to create the next generation of intelligent device solutions with embedded machine learning. Get your free account at edgeimpulse.com. Maxim Integrated, enabling edge intelligence with sensors, signal conditioning, low power Cortex M4 micros, and advanced AI acceleration, I believe. Kixo AutoML for embedded AI, automated machine learning platform that builds tinyML solutions for the edge using sensor data. Reality AI, engineering solutions for the edge. Next generation AI tools for product development. SynSense builds ultra low power sensing and inference hardware for embedded mobile and edge devices. All right, thank you to our sponsors again. And just a reminder for the next tinyML talks that's coming up on September 15th. And also please check out tinyml.org for the 2021 tinyML Summit information. Thank you, everyone.